student of mine now at Oklahoma State University. It's got keywords in it, conformal geometry and GR, I think. And then there's an article which is sort of a conceptual background to some of the things with Andy Chack and Matthias Hammerl to do with holonomy reductions in this Cartan type setting. And that in turn is linked to some earlier work of mine, which was kind of purely in the conformal setting. And actually, although I want to sort of motivate thinking in general about things, I'll keep myself to the conformal setting. So, you know, with the scope of just 3 lectures, I thought it's good to be sort of focused in that sense. However, everything will be very elementary, especially at the start. And in a sense, the main idea will be to get the motivation for things, because with sufficient motivation, you know, you can sort of do it yourself. So let me do the next slide. So here's one of my favourite pictures. The scope of lecture 1 is going to be just sort of very basic things. So I hope you don't feel I'm insulting your intelligence. But really the way is to, as I say, to build motivation and understand what we mean by geometry. We'll talk about basic geometry, conformal geometry, and the Riemannian model of that. And also actually the pseudo-Riemannian model, and then the tractor connection and applying it to prolongation. So I just wanted to mention prolongation today, but that won't be a main thing. So the following after that we'll talk about sort of tomorrow's lecture, or the next one will be geometry of scale, which is in some sense how to go from conformal geometry back to Riemannian or pseudo-Riemannian geometry, but in a sort of insightful way, and the idea of compactification. And we'll also touch on compactification today, and then in the final lecture, so that'll be lecture 2, and then in lecture 3 we'll talk a bit about sort of hypersurfaces, so submanifolds of codimension 1. Because that's linked to this compactification picture, and then the application of the 2 ideas to what I call boundary calculus and the construction of like boundary invariance, holography, and so on. So I think things will sort of slowly speed up. Okay, so that's sort of where we'll go, but today's very elementary, hopefully. So yeah, what about this picture? So one thing is down here, I'm saying that I'll often be in dimension D, and we'll think of that as n plus 1, because n will be the boundary dimension if you have a manifold with boundary, for instance. And here's a picture. Well, I'd like to say this arrow is pointing at Brno, but those of you who saw me say this a few weeks ago, I said it was pointing at Warsaw. But it's a pretty blunt arrow, so let's say it's pointing in this region. And of course, most of you have seen this picture before. You know, the idea is you give one of your Brno surveying students a sort of flaming torch that is tangent, and you ask the person to carry it around the world in this way. So you ask the surveying student to keep it parallel to itself, but otherwise tangent to the Earth. You go up to the North Pole, take, say, a right angle, and head down to, sort of west of South America there, and continue across, and then come back up. And then when you get up here, the thing will have turned a right angle. Well, that's actually the person who really did this started down in South America, sort of halfway up Brazil there. But it's turned a right angle, and that's holonomy in action. So this vector is following. Well, it's following the induced connection that you get. So we're in ambient Euclidean space, and then by projecting, we're getting the connection induced on the sphere. And as probably you all know, that agrees with the sort of intrinsic Levi-Civita connection of the sphere. So that's why the students working in that connection locally on the world. But this sort of thing that it's turned a right angle is an example of curvature, or as I said, holonomy. And as I said last time I was talking about this, this is, in a sense, the origin of the word plain sailing. So, you know, if you just sail around in a small area like the Gulf of Mexico, the interior of angles of a triangle add up to 180 degrees and so on. But as you can see on this triangle, the internal angles don't add up to 180 degrees anymore. So plain sailing, so which should really be spelled with, you know, it's spelled both ways if you look it up, but it should really be spelled like that. It's when you're sailing in a plane, right? So it's also, therefore, the origin of it's then easy. But if you do that on the big oceans, you get lost. So one of the reasons I wanted to mention this is that, in a sense, this captures a lot of the ideas that I'll be talking about. So in one sense, things don't get more complicated than that, even though they would appear to. Right. Okay, so we talked about Euclidean geometry. The other obvious thing you can do, so Euclidean geometry comes from the dot product, you know, so you'd be summing from I equals 1 up to n. I guess I'm in dimension n here, didn't make the change, with all plus signs, but then if you put some minus signs in, then you get what I call a pseudo-Euclidean metric. And here it would have signature PQ. And in particular, a sort of most famous case comes from the Minkowski inner product, where you just put Q is 1, so you get one lot of minus signs. Then there's null vectors. So the interesting thing that happens is that you have some vectors that are not themselves 0, but they have sort of length 0, if you like. So they have 0 inner product in this metric. And in fact, you get a whole null cone of them. And I guess you're all familiar with this sort of thing. And this is fixed by the group that we call the orthogonal group n-1, 1. So this preserves this null cone. And so, for instance, in dimension 4, where you have E31 in this notation, this is what is used to model a space-time where the speed of light is constant in all frames. Because if you change your, you change your reference frame, you use this group to do it, but it preserves this null cone. And if you do the calculation, what that means is that you might have changed to a moving frame, but the speed of light is still the same. So that just comes out simply from this. And another important thing about this is that this was motivated by the observation, the actual observation that the speed of light was the same, which in turn was motivated theoretically by electromagnetism, where they had the equations of electromagnetism that they noticed suggested that the speed of light should be the same, but no one believed it would be. So they did these Michelson-Morley experiments. Okay, so continuing our elementary sort of picture here, this is all vastly generalized, although still elementary from the point of view of this conference, I suppose, by what's called pseudo-Riemannian geometry. So what you have then is a manifold, which as usual we view as a type of surface, if you like, but in high dimensions. And in the tangent space at each point, and that's what I'm trying to indicate with this diagram if you can't see it well, you ask that the tangent space be equipped with a pseudo-Euclidean inner product, just like I had on the previous slide. But so it's equipped with the sort of dot product that has a signature, but it's in a way that's point dependent. In other words, in each tangent space you have a type of dot product, but there's no obvious way to identify the tangent spaces at different points, so necessarily you end up with a point dependent inner product. And the idea of general relativity as a sort of motivation again is that space-time is well modeled by a Lorentzian signature pseudo-Riemannian manifold. So the idea is that gravity and the path of planets and things is coming from the curvature of such objects. Okay, so but now let's get down to some of the sort of nitty-gritty of what you would want to do from that. If you want to do local geometry and analysis, then what happens? Well, and again I'm assuming that secretly you know all this, so the metric determines a unique Levi-Civita connection, so some sort of connection. So it's the unique torsion-free connection that preserves the metric. So that gives a way of transporting vectors along curves, like we saw on the map of the world, right? So that was a connection, if you like. Our surveying student was using a connection to transport the flaming torch around. And then from the connect, so you've got the metrics determining the Levi-Civita connection, and then there's a notion of curvature, as usual for the formula for the curvature, and then you get invariance and so on. And so in Riemannian or pseudo-Riemannian geometry, we often call this the Ricci calculus, and because it's all sort of historically well known, we think of that as easy. You could generate natural operators like the Laplacian. How is that made? Well, we have this geometrically determined Levi-Civita connection. You contract the indices together using the metric again. That gives you the Laplacian or the rough Laplacian if you're acting on a vector bundle. And then you get sort of equations naturally. So the Ricci curvature being proportional to the metric is a sort of natural equation. That's the Einstein equations. So that's what happens in pseudo-Riemannian geometry. And so we think of life as easy, but we'll come up to conformal geometry where the first step is at least a little more complicated. All right, but now I want to just touch on, I said tomorrow I'm going to talk about compactification, so I just want to sort of glimpse ahead and think of this as a motivating problem to make us even think that we should do something other than just Riemannian geometry. But the interesting thing is that, in a sense, I want to phrase it within Riemannian geometry. So, sometimes I think people who are working in Riemannian geometry would want to think of conformal geometry as somehow, arcane or perhaps not necessarily useful. I've even had conversations with people saying, tell me something useful that's come from conformal geometry. I remember having a discussion with someone who's actually quite famous asked me that question. So let's think what are some of the things in Riemannian geometry that motivate this. So one of them is this very obvious thing that Euclidean space is too big, right? So here's, for instance, perhaps that's the Euclidean two-plane. Think of it as the top of this desk, but it just continues on forever, right? So just take a moment to just really, because we deal with things like Euclidean space all the time, and we forget that it actually goes to infinity, right? So that's a problem. For instance, suppose you had some sort of field on your Euclidean space, and you wanted to evolve it in time, and you went next door to the applied mathematician and say, okay, I want to. You set up some applied equations and solve them in time. So you would approximate it perhaps with grid points. What are you going to do with the grid points as you go to infinity? So you can't have them equally spaced, right? You're going to run it on a computer. So it's just too big for some purposes. But that's thinking of it as a sort of applied maths problem, but the same issues show up in analysis. So if you're going to deal with functions and you want to evolve something or something like that, then you're going to have to assume some sort of decay or behavior of your functions as you go to infinity. So what's a sort of good way to get a handle on that? And that's what compactification is about. Okay, so how do you treat all of that mathematically? And then one way to sort of deal with this is to add some more points, right? So it was already too big, so you add some more, and you do what's called a compactification. So the point is that Euclidean space is non-compact, and we'd like to compactify it. So, of course, the most obvious compactification that, again, you will know about is stereographic projection. So you sit your medicine ball on your Euclidean plane that goes off to infinity. You can do this in any dimension, of course. And then you identify the plane with the ball by taking the north pole of the ball, here it is, and then you take the straight line that goes from the north pole, goes through the sphere, goes down and hits the plane. So you identify that point on the sphere that it went through with the point on the plane. So it's easy to see that, of course, this is a one-to-one map. It's even a diffeomorphism. You can, with the usual smooth structures. What is not so obvious, but can be your first exercise if you haven't done this before, is that it's actually conformal. So what I mean is that it preserves angles, right? So it obviously doesn't preserve lengths because infinite distances get mapped onto the whole sphere, but it preserves angles. So the thing is, this whole infinite sphere gets just, infinite plane gets mapped onto a sphere. Now I've moved up to dimension n plus 1, so d, and it's a one-to-one map just onto the compact sphere, except you miss the North Pole, and the North Pole gives you your infinity for all of the lines, for instance, that go off. Okay, so here's another one. So this is a compactification of Minkowski space. So Minkowski space, again, you should think of as a plane, or a d-dimensional plane or whatever, an n-dimensional one. But now equipped with this Minkowski and a product on it. So there you go. So it sounds like the same problem, and we want to compactify it. Well, it's well known that you can conformally compactify Minkowski space, and the usual picture that you'll see in GR books or something is this Einstein cylinder. So somehow this flat plane can be compactified into this region of the cylinder, and so this cylinder is equipped with the sort of obvious Lorentzian metric, so minus dt squared plus the sort of sphere metric. Okay, so there is a conformal map so that obvious sphere metric is conformally related to the flat Minkowski space. Now some questions are coming up, right? So with the previous one, it was a one-point compactification, and now the compactification has some interesting features. So this point here, I plus, is future time-like infinity. So all geodesics that are time-like, sort of heading into the future, end up at that one point. I naught, which is 1 point, is space-like infinity. So all of the space-like geodesics end up at this 1 point. And then there's a past time-like infinity, and all of the null geodesics end up on this open region on the boundary that they call scry often. Okay, well, there's actually two copies in Minkowski space, so the other side of this is another copy. But anyway, the point is this the only way to conformally compactify Minkowski space, or perhaps are there others? Do these things have to be isolated points? Why is the null region an open region? And why does this picture look quite different to the Euclidean picture? So we had a 1 point compactification, and now we have all this. So, and even going back here, so this is a 1 point compactification of Euclidean space. It's conformal. You might say, well, are there other conformal compactifications of Euclidean space? Perhaps you might think you can compactify Euclidean space and have the boundary be a hypersurface or something. Right? Is it restricted? So we want to understand all of those sorts of things, right? So those are the sorts of, those are some sort of questions. And then I guess my point of view is that we won't understand those things if we don't understand conformal geometry. So I'm thinking of this as a motivation. So here, I'm just repeating those questions. So conformal geometry, roughly speaking, is geometry with angle but not length. Okay, but I want you to think of not just Riemannian signature, even though I'll often be working in that signature. So we have to be a little more precise. So a conformal manifold will consist of a manifold and a thing I'll call C, and C is going to be an equivalence class of metrics. So metrics are said to be equivalent if they're related by multiplying by a positive function squared, right? You square it to make sure it's really positive. So we think of that as a smooth function. And this can have any signature. I'm going to be working in dimensions greater than or equal to 3 for that. So as you may know, conformal geometry in dimension 2 is a little different. Although, I mean, this part of the definition works the same, but some aspects are different. So at the moment, we could be in any dimension, but for a lot of what I say, we'll be in dimension at least 3. Okay, so what have we got now? So again, we've got a manifold.
I have a question.
Okay.
Maybe stupid, but Parallel's construction of the Minkowski space is open in SU22 mod, the compact.
Say the question again.
So Parallels constructs the Minkowski space inside the group SU, special unitary 2, 2, over the compact, the maximal compact. I was wondering if this is inside this theory, because that compactification is not one point, you add the quadricle. No, you're not.
I see. Well, I'm not going to talk about that, but
sorry about that.
That's all right, but it would, yeah.
Okay.
If it works, it's just a slight variant.
Right.
Yeah.
Thank you very much.
In a sense, I could come back to it. Okay. So what's happening in the tangent space at each point now? So before the tangent space was Euclidean space or pseudo-Euclidean space. So now the tangent space is it's like pseudo-Euclidean space, but we're allowed to dilate as well. So in Riemannian signature, it's actually just like you were doing at school. You had similar triangles, they had all the same angles, but they were allowed to be different sizes. So in Riemannian signature, that's what's happening in the tangent space at each point. You have that sort of similarity, but it's allowed to be point dependent as you move around the manifold. Okay, so what about some other motivations for conformal geometry? Well, there's really quite a lot. I don't think I'd probably be preaching to converted here. But one thing, as I said, the equations of electromagnetism are not just Lorentz invariant, that motivated the Michelson-Morley experiments, but they're actually conformally invariant. So the very motivation that led to these experiments of Michelson-Morley could have also led to people saying, well, shouldn't physics and space-time and everything be conformally invariant? And in fact, this is a sort of partial theme in physics as to whether or not there is an element of that. Some more evidence is that the Yang-Mills equations that govern the weak and strong force are, in their natural setting, conformally invariant as well in dimension 4. The ADS-CFT correspondence, for those of you who know what that is, the anti-de Sitter conformal field theory correspondence uses a lot of conformal geometry. In mathematics, two-dimensional, so Riemann surfaces, which are two-dimensional, so one-dimensional complex manifolds, so two-dimensional in the real sense, are conformal manifolds. And then if you take domains in CN, so sort of smoothly bounded domains, then the boundary picks up what's called a CR structure. So when you're studying such domains, you're interested in the invariance up to biholomorphisms of those domains, and then a certain amount of the boundary geometry is preserved, and that's called CR geometry. There's some sort of further details to go into that. And that's almost conformal. So I won't go into what that means, but you can ask me later if you want. My theme will be more to do with the fact that conformal geometry just has a deep role in ordinary pseudo-Riemannian geometry. This is well known through things like the Yamabe problem, which sort of involve conformal transformation. This is the problem of finding constant scalar curvature metrics by conformal change. But also in symmetry and dynamics, and as I'll be talking about here, a tool for compactification and therefore a use in scattering and so on. All right. So we're motivated. All right. So that's the sort of motivation part. Now, just here's a sort of technical slide. I don't want you to sweat on this at the moment, but I guess you can chase it up at the tutorial a lot if you want. But one thing that in conformal geometry, important role is played by density bundles, and that'll turn up also in a lot of these Cartan geometries that will be talked about. So why does that happen? Well, on any smooth manifold, you can form the top exterior pair of the tangent bundle. Why not? Right? So you're wedging the tangent bundle to itself. And that's a line bundle, right? So if you're in dimension D, the top exterior pair is a line bundle. And if you square it, then it's even an oriented line bundle. It gets a canonical orientation. Now, in Riemannian geometry, that bundle's just trivialized because the metric determines a volume form and it trivializes that bundle, so it doesn't really have an important role important, doesn't have a sort of active role in most things you do in Riemannian geometry or pseudo-Riemannian. But of course it's not trivialized canonically when you just have a conformal class of metrics. So that's why you should sort of involve this line bundle in things, and it really needs to be involved. So when you try and construct invariant operators and so on, there won't be many conformally invariant operators if you don't notice that these bundles are around. Okay, so one of the things that we will use, but I don't want to sort of overdwell on, is that there's a conformal metric. So I was saying that a conformal geometry, you have equivalence class of metrics. So metrics that are related like that, conformally related, are said to be equivalent. You have an equivalence class. So there's no metric, but there is a conformal metric. So with this notion of density bundles, there's a section, so that should be a section of that really, of the symmetric square of the cotangent bundle of weight 2. So if you allow this conformal weight, then there is a canonical object in there. And you can think of it, the dth power of this thing as the thing that's mapping you from this top exterior power squared to the density bundles, if you think of them as a line bundle. Okay, and then once you have this object, there's a one-to-one relation between sections of densities of weight 1, sections that are positive, that's what the plus means, and metrics, just by taking the metric which is sigma to the minus 2 times this conformal metric. So the conformal metric has weight 2, sigma has weight 1, sigma to the minus 2 has weight minus 2, so you end up with something of weight 0. That's the metric corresponding to the section. And we call this a strict scale. So the Levi-Civita connection for the given metric G, say the one that we just found there, acts on these densities through this isomorphism. And so it's easy to see that tautologically it then preserves the density that was used to determine the metric from the conformal class. Because it's that's giving you the map through, and the way the Levi-Civita connection acts on sigma is via that map, and then if you just chase that through, it just follows trivially that that the Levi-Civita connection that sigma determines is then preserves sigma. So we will use that a few times. That's the main reason I want to mention that now. Okay, so let's get back to this sort of slightly less technical thing. Conformal geometry it's not as rigid as pseudo-Riemannian geometry. I mean, in the literal sense, if you make a Riemannian object, it's sort of if you like a bit stiff, like a house, but a conformal geometry is more floppy, right? So it has one function's less information in it, if you like. So that this is very good for some purposes, but it complicates analysis. So in particular, there's no metric on the tangent bundle, and therefore no Levi-Civita connection on the tangent bundle. And if you're just in conformal geometry, there really is no distinguished connection on the tangent bundle. Okay, so you're stuck for making things like the Laplacian. What you can do is pick a metric from the conformal class. So you say, oh, well, we have an equivalence class of metrics, so let's pick one and use its Levi-Civita connection. And then you have to see what happens when you change your mind about your connection from the conformal class. So you conformally rescale it.
Sorry, question.
Yep.
You say that there is no metric, but then you say that there is an equivalence class of metrics. I guess these metrics are defined
up to equivalence. Yeah. Yep.
No, in some point there should be not defined, because you say there is no metric.
Yeah, what I mean is that there is only an equivalence class of metrics. There's no distinguished one. You have
the metric?
Yeah, well, you have them or you don't. I mean, you have what a conformal geometry is the manifold equipped with an equivalence class of metrics. So you have metrics from your equivalence class. It consists of metrics, but they are not canonical. They're a choice, right? It's like you say you have coordinates locally, but they're a choice.
They are defined everywhere.
Yeah. I'm not dealing with the, saying that there's no metric everywhere or something like that. I'm just saying it's an equivalence class. Any other questions? Okay. So what we have to do is understand what happens when we move from one metric to another in the equivalence class. And what happens is, well, a mess, right? So you start off with one Levi-Civita connection. That's for the metric G. What happens if you want the Levi-Civita connection for this G hat, which is S squared G? Well, they're related like this, okay? So where this one form upsilon is the derivative of the log of that function, that positive function.
And by error terms, you mean all the upsilon things?
What's that?
By error terms, you mean all the
Yeah. Did I even say error terms? I probably did. But yeah, this is how they differ. So there's all of this stuff. So for example, the Laplacian, if you want to do analysis, the people want a Laplacian. So how does that change? Well, it changes by this formula, right? So if you're acting on a function u, then you get this formula. So dimension 2, it's not too bad because this drops off and it's covariant, right? But in all other dimensions, you get a mess, and you want to try and fix that somehow. Also, here's the error terms. Yeah. So this stuff on the right-hand side, that's what I'm calling error terms here. This increases exponentially with the order of calculations. So you can calculate like this, up to order 3 or 4 or something like that, and then it gets really painful, and so you might say, well, I'll use maple or something, but sort of maple blows up even at order 8 or something like that. So it gets out of hand quickly. Okay, so well, the solution. We've already, we're here talking about Cartan, so of course Cartan is the solution. So there is a metric and connection on something slightly bigger than the tangent bundle, right? So that's going to save the day. So what I want to do here is, I was reminding myself, is motivate where this comes from, or understand where this comes from. Okay, well, I said that the world one was my favourite picture, but probably this is my favourite picture. Many favourite pictures. So, so this is a sphere being born, but it's being born with a conformal structure, right? So, the thing is, a lot of people think of conformal geometry as you have a metric and then you forget about the scale, so you're allowed to change the scale of your metric. But that doesn't make you feel that conformal geometry just exists naturally. So here it is, right? So I want you to understand how the conformal sphere arises as the ray projectivization of the forward null cone, right? So what do I mean? Okay, so here's our RD plus 2. Why not? Everyone knows what that is. And I'm equipping it with a Lorentzian signature metric, like we were talking about at the beginning. And then, as I was saying there, we get a null cone. So this consists of vectors whose length is 0, right? So you get a cone of them, and it's also a pass cone. I'm just giving you the forward bit. I'm sort of thinking of it as a time orientation or something. So this is half of the null cone. Okay, now what I want to do is a ray projectivization of that. So each null ray going up this cone, I want to map to one point. Okay, so just like when you do usual projective geometry, as like was mentioned in Boris's talk, lines would become points. But here I'm just going to take these rays and make them a point. Okay, so fairly obviously you get a sphere, right? So one way you can see that is just take a section, the sort of obvious section across here, and you'll see that you can even make it be the round sphere. Okay, so topologically, when you do this, you get a sphere. Now, is this the duster? So I claim that this gets a conformal structure. So how do we see that? Okay, so here's our null cone, and then we're doing this projectivization, and we're getting a sphere. Now what you do, this is actually a ray bundle by construction over this, right? So it's a ray bundle. So this is the bundle map, if you like, and I can take a section of the bundle map, let's call it sigma. And then that gives me some section of the null cone. Now on that section, I can look at the tangent vectors and evaluate the tangent vectors using this, this Lorentzian inner product, right? And that'll actually induce, on the sphere, some metric G induced from that. And it's quite easy to see if this is actually a section, that this is then a Riemannian signature metric. And what happens if I choose a different section, sigma hat, say, so G sigma hat, well, what happens, of course, in the theme of the talk is that they're conformally related, right? So there's a positive function relating them. Okay, so, well, we didn't have a section of this, we just have the projectivization. So what you actually have canonically is a conformal structure. So, so this sphere born this way has a conformal structure and not more. Okay, so, so on this sphere we don't have a canonical Levi-Civita connection, we only have an equivalence class of them, and we would be stuck for doing analysis and so on. But we can go back to this picture and see that actually we have a lot of good stuff here that we haven't used. So in particular, the affine, so Rn plus 2 is a vector space, so in particular it's an affine space. So it has a canonical parallel transport, just the transport where you carry things around in their components as being constant. So, so there is a parallel transport on Rd plus 2. And it's easy to see that actually this gives a conformally invariant connection on the sphere. So what you do is you say, well, we have parallel transport over here, and you take tangent vectors that live in d plus 2 we're doing, restricted to this cone. What do I call it? N plus or C plus N plus. And then you mod out by the equivalence that if they're on the same ray and parallel, then you're going to identify them. So I mean really parallel in the sense that they have the same length and everything. So you're going to identify them, and then that gives you a vector bundle on the sphere. So that gives you a vector bundle, which is that equivalence class. Right? So that's your mod that equivalence relation. But then the parallel transport on Rd plus 2 gives us a parallel transport of that vector bundle. This metric induces a metric on that vector bundle. It's obviously parallel, right? It's constant. And this metric is, so it's preserved by the connection. Now, so we do get a canonical connection, but it's just not on the tangent bundle, it's on this higher rank bundle, right? So we get a connection on the tangent bundle, and it has the structure that it's like the tangent bundle, but with two more dimensions. So it's sort of R direct sum the tangent bundle and R. So what are these other two dimensions? Well, we have, for instance, the directions going up the fibers, right? That's a sub-bundle sitting in this tangent bundle. We have the tangent bundle to the cone itself, which is a sub-bundle of the whole thing, and then we have directions going off, right? So that's where you can see the extra two dimensions coming from. Okay, so all together we have that structure, and this is obviously filtered, so vertical direction sit inside the tangent bundle, sits inside the whole thing. So it's a filtered structure. Whoops. Okay, yeah. Just for fun, what about if you do this in other signatures? That was the Riemannian model. If you have a physics bent, you may be very interested, for instance, in the Lorentzian model or other signatures. So here, what happens if we start with Rd plus 2, but now instead of with the Lorentzian thing, we have two minus signs. Then when we do this, well, we take this null quadric, right? Just like the picture here with the null cone, but now the picture has a different topology. So I've put these on the other side. So So the quadric is given by this formula here: x naught squared plus x1 squared equals the rest of them squared. And so the ray projectivization, if we take a section of it, one of the sections is you take the left-hand side equals to 1 and the right-hand side equals to 1. So obviously that section is S1 cross Sn. And then it's easy to see that that's then getting induced on it, the Lorentzian metric that I talked about. So you'd have minus gt squared, if you like, plus the sphere metric. Okay, so that's in the conformal class, and so this gives you the conformal model that includes that sort of obvious Lorentzian metric. So the tractor bundle on that has signature D2, where as usual D is n plus 1. Okay, so we'll come back to this tomorrow, when we're trying to understand compactification. So I want you to sort of remember that. Okay, but anyway, in general, as Boris mentioned, 100 years ago, Cartan sort of realized how to make an invariant connection in conformal geometry. Thomas had a sort of view of this that's more related to the way I'm talking today, so motivated by this picture here. In either way, they're basically the same thing, and in this article with Bailey and Eastwood way back in '89, we sort of wrote down an explicit calculus that if you like, develops things from the Thomas point of view, but in a modern sense. So the result is that on a conformal manifold, you get a tractor bundle that looks just like this model, right? So it has those dimensions, it has that filtration structure, it has a conformally invariant connection, and that preserves some Lorentzian signature metric on it if you started in Riemannian signature, or a p plus 1, q plus 1 metric if you start in PQ. Okay, and then importantly, there's this canonical or position tractor that gives the filtration structure of this tractor bundle. So it canonically puts the densities of weight minus 1 into the tractors, or gives you the projection out. And that was the thing coming from the Euler vector field in the model. Right? So you had that Euler vector field as the canonical object. Okay, so okay, well let's now sort of write down how this comes from prolongation. So this was in the article with Bailey and Eastwood, that's how we did it. So let me remind you of that. So a metric, start off with a metric G, take a conformally related metric where I'm going to make the conformal factor minus 2 instead of plus, right? So u to the minus 2, u is some positive function. So that metric will be Einstein, meaning for this lecture that means Ricci is some constant times the metric, right? If you assume it's a function times the metric, in the dimensions I'm talking about, it's supposed to be a constant anyway, by Bianchi. But anyway, it's Einstein in that sense, and then you work out the conformal transformation that's coming from that, and you see that what it means is that you get this overdetermined second-order Hessian type equation, the trace-free part of two derivatives of u plus the Schouten on u is 0. So the Schouten tensor is a trace adjustment of the Ricci tensor. I'm hoping everyone knows what the Ricci tensor is. But so here's the trace adjustment formula. Ricci is, that should be a d plus 2 if I'm in dimension d, sorry. But in dimension n it would be n minus 2 times Schouten plus g times j, where j is the trace, the metric trace of Schouten. Okay, so it's just a trace adjustment. Okay, now to study this, it's best, again I can explain this more if you want, but it's best to drop the positivity of that function. So if we want it to be a metric, then obviously we want u to be not 0, but I want to drop that requirement and just allow u to have any sign and just be a solution of that equation. And it's best, in fact, to replace u by a density of weight 1. Because when you replace it by a density of weight 1, this equation becomes conformally invariant, right? Otherwise, it's just sort of covariant. And then we study it by prolongation. So what's that mean? Well, it means what we do here, right? So in prolongation, you want to make an equivalent first-order system to your partial differential equation. So here's, here's your partial differential equation. So the first equation is just renaming the derivative of sigma so that u has become a sigma. I'm calling it mu. So the second equation now is this one here. So this is trace-free. In other words, that equals, you know, the metric times something. Or I'm using the conformal metric because I'm using densities. So that equation becomes the derivative of mu plus Scouten times sigma plus something to absorb the trace, right? So the trace part, the metric part, or the conformal metric part. So with these two equations, the system's almost closed up as a first order system. The derivative of sigma is given in terms of mu, the derivative of mu is given in terms of sigma, and rho. Okay, so what we don't know is what's the derivative of rho from the first two equations. So you're doing almost nothing up to there, but then you want to know the derivative of rho, but you can just, let me say, play around, and that's going to be your second exercise, and see that the derivative of rho is actually given by mu contracted into the Scouten tensor, right? So that finishes the prolongation because now it's a closed system. Okay, yep?
Can you elaborate on that third term in the second equation? How would I guess that that should be included if I'm doing the prolongation?
Which third term, the rho?
Yeah.
Well, it was already up here, right? Because that was the trace-free part. So this is the trace part. So if I say that you have TAB is trace-free, that means that TAB is rho times GAB for some function. That's all.
I see.
Yeah.
Thanks.
Yeah. So that's where that came from. So that was sort of for free. Any other questions? Okay. So yeah, so your exercise, which is pretty easy, is to differentiate the second equation and find out that that's what happens in the third one. Okay, but now it's closed up and you've rediscovered the tractor connection, because it turns out that this system can be collected into a conformally invariant connection. So first of all, the system had those three variables, right? So the sigma, the mu, and the rho. So the sigma, the mu, and the rho. And so you get a bundle of rank d plus 2 if we were in dimension d. I seem to have gone back to n. Something went wrong with my slides here. So let's say n plus 2. I'm giving the densities in terms of n. And that system of equations, let's go back. So I'm just recollecting them into something which forms a connection, right? So if you look at those equations and you see here they are. If I put this equals to 0, that's those system of equations. Grad sigma equals mu, the original equation now with mu involved, and then that formula on rho, as I said. Okay, so that gives you a connection, sort of obviously, because each of the first terms in here is the Levi-Civita connection acting on those things. And then the rest of it gives you an endomorphism of those variables back into the same bundle. Okay, so we've constructed a connection. You can check it's actually conformally invariant, so if you change your mind about the metric, things will transform in the right way. And this connection preserves a metric, and here I'm writing it as a quadratic form. So you can just check that, first of all, that this formula here is conformally invariant when these components transform the way they have to. I'm leaving out some of the details about how they need to transform, but all of those sort of additional details, for instance, are in that article with Sean Curry. So there's like a guided tour through the details of this in there. And another important object is this Thomas D operator, right? So we've finished making the tractor connection. This is the thing that's equivalent to the Cartan connection. That'll be one of your exercises to show the equivalence. But there's also another tool that comes up with this second order operator. So here, if I'm starting with a density, this is mapping it to some numbers times the density, some numbers times the derivative, and then this Laplacian term, right? Now, actually, if instead of a density, I make this a tractor with a weight, so any number of tractor indices, the same formula works if I use the Levi-Civita connection twisted with the tractor connection. This is still invariant. Okay. So these objects, the tractor connection, the tractor metric, and this Thomas D, that's like your starter pack for conformal geometry. You can you can now go away and do stuff, right? You can actually calculate. So you know, what sort of things might you want to know? Well, the classic questions are to do with, for instance, making invariants and invariant equations. So here's an exercise. Well, the first bit is almost trivial. So suppose you start off with a density of weight 1 minus DO2. I'm back to dimension D. I'm sorry about the dimension switching. And H, a density of weight 2 minus D over 2. Well, let's look at the first one. What happens if I put that in here? Well, if the weight is 1 minus D over 2, that term is 0, that term is 0, and this makes this exactly the usual Yamabe operator, right? So the first bit of the exercise is done for you. That's the Yamabe operator appearing in the bottom slot. The second one you have to really do, but if you do 2 Ds on there, then you'll get all zeros, and in the bottom slot you'll get this sort of famous Panizzi operator, which is Laplacian squared plus lots of lower order stuff. Okay, so it's a bit of a surprise that all of this stuff goes in that case. So it's a calculation, and it relies very much in this case on it being a density that you're acting on, right? So if H were a tractor and not a density, that's not true. You have to commute derivatives to get those zeros. Okay, but anyway, you see that you're getting somewhere because the Panizzi operator was only discovered around 1980 or something like that. It was independently discovered in like 5 places around that time, so Panizzi got his name on it. He deserves it because he passed away shortly afterwards, so why not? Yeah, so that was only discovered, so recently, but you can just, rediscover it like this. Now, the D in the general doesn't commute with itself, and if you do DADB, that means a commutator bracket. You'll get some stuff, amongst which is a thing we call the W tractor. Okay, so there's some sort of curvature I'm indicating that comes from this, and then that curvature, because it's got all tractor indices, you can apply this Thomas D to it. You can apply the Thomas D to it twice or 411 times, whatever you like. And then you can contract these things for themselves. This proliferates invariance of your conformal structure, which was one of the classical questions, asked even by people like Pfeffman and that. How do you make something like all invariance, right? So this is, with a little bit of extra embellishment, this gives you a way of making nearly all conformal invariance. So you start to get somewhere. Okay, we've got some other things to say. I'm going to run out of time probably, but one of your exercises as a pause here is now to take this tractor point of view and go back and make the principal bundle and the Cartan connection on it. So Boris told you that the rules for a Cartan connection and so on. So you'll see that you can actually reconstruct that from the tractor bundle in a sense quite easily if you know what you're doing, and the solution is in this article with Andy Chapp if you want to look it up. But the sort of rough idea is much simpler than what's written there.
Sorry.
Yep.
The bracket in there, because
yep.
the D is not a first order operator.
Yeah. So the ... dot's important, and I'm just not telling about that. So there's some other complicated stuff here. So this W tractor is just like a curvature. So in fact, if you know about the ambient metric of Pfeffman-Graham, this is really the curvature of the ambient metric, but brought down as a tractor object. So the ... here means that that the bracket of the second order operator is not as you said, second order is not a curvature in the usual sense. But this is one way to get it. There's another way to get it via tractors, and it just looks complicated. But I can talk about that. Okay, so I want to just finish with a brief look at prolongation, because we use prolongation to construct the tractor connection. But prolongation is actually important for lots of problems. So every time you have an overdetermined, say, quasi-linear differential equation or something, if it's really overdetermined, you should you should certainly do prolongation to help you study it. But especially if it's linear. Now, I don't want to talk about anything complicated because, we're meant to be simple here. So let's just look at the conformal killing equation. Right? So this is one of the simplest equations that's in this category. So the conformal killing equation is the equation that says the Lie derivative of the metric is proportional to the metric. Right? So that's a sort of obviously a conformally invariant statement. Okay, so K here is a vector field. So if you have a vector field such that along that vector field the Lie derivative of the metric gives you a function times the metric back again, that's called a conformal killing field. Now it's an easy exercise to rewrite that so that the equation, so that can be another one of your exercises, just using the definition of the Levi-Sever connection, it becomes that the trace-free part of, you take the derivative of the vector field, you symmetrize, that's what these round brackets mean, and take the trace-free part. Okay? So put that equal to 0, that's the same as that equation. This way it's sort of obviously overdetermined because we have just these n variables, but you have, n plus 1 over 2 minus whatever for the trace, so minus 1 number of equations. So it's overdetermined. And whenever you have an overdetermined equation, it's good to study it by prolongation. So we could start playing the game like we did for the case of that Hessian equation we used to discover the tractor connection. So you would you say, oh well, the trace-free part of this is 0, and that's a symmetrization. So if we don't symmetrize, then this is equal to something skew, that's the mu, plus a trace part, that's that bit there. And now we're, once again, it's so simple that our system's, not that far from closed up. The derivative of K is given in terms of mu and rho. So we just need to work out what the derivative of mu is and the derivative of rho. And when that closes up, that's your prolongation. Now this case is so simple it's not hard to do it by hand, but there's still a little bit to do. And there are decisions to make about what variables to introduce and so on. So one of my points is that you don't actually have to make those decisions, that the tractor connection makes them for you because this is conformally invariant. So once you have the tractor connection, you can use it to actually do the prolongations of conformally invariant equations more or less automatically. Okay, so, but there's a most obvious way to do that, but I want to talk about the second most obvious, which becomes a sort of effective calculational tool. So, first of all, you observe that if you have any vector, then what I'll call its half prolongation puts this in the middle slot of a tractor. So you put 0 in the top slot, put the vector in the middle, and its divergence in the bottom with that formula. This is conformally invariant. It satisfies the right transformation to be a tractor. Right? So it gets a tick, and you go and have a beer and come back to work on it. Okay, so an exercise is that you say, oh well, this wasn't very tractory, you had to do something here. So another little exercise is that you can come to this thing just purely using the tractor stuff. I'll leave that as a little exercise to think about. Okay, so that's the half prolongation. And then, with the half prolongation, you hit this with this Thomas D operator. And it's actually quite easy to show. So you can either calculate, or you can do this almost by pure thought, that this Thomas D operator acting on K is skew if and only if the conformal killing equation holds, right? So this sort of looks like the killing equation now, but we've removed the trace term, but that's sort of built into the tractor part, right? So that's a little exercise, and then a consequence is what I call the full prolongation, in other words, the closed system. So K is a conformal killing vector if the derivative of the skew part of that thing is equal to some curvature acting on K, right? So one of your exercises will be to calculate this curvature using this method. And the answer's back in this paper, but it's quite easy and you'll see how to do it. Okay, so where does that come from? Well, first of all, this is just a straightforward calculation. So once you've made that K, this would be an obvious guess that this would happen. And notice that this is conformally invariant. So we haven't prolonged fully, but we have stayed in the conformal world. Okay, this is the last slide, Jan, sorry. So in the conformally flat case, how do we see what's happening here? Well, let's do two Thomas D's on K. Right? So if it's killing, if it's conformal killing, then the first Thomas D on K is something skewed. Right? On the other hand, if we're in the conformally flat case, these Thomas D's commute with each other. So these two Thomas D's on this half prolongation live in the bundle which consists of things which are symmetric on the first two indices and skew on the last two indices. And that's the zero bundle, right? So an exercise is for you to show that when you intersect those things, that's zero. So this is one of the key ideas in prolongation. And so you see in the flat case that this is zero. In the curved case, this is not zero, but you just perform the calculation that shows that that's zero in the flat case, but now keeping track of the commutator brackets, and that produces the curvature term. So that's the green exercise. Then going back is easy. Once you have this equals curvature or zero or whatever, the top slot just gives you the equation back again. Okay, so the moral is that you can, once you have the basic tractor connection, you can actually use that to do prolongation on more or less any other conformal invariant equation. And this is an idea that works quite generally and has been, I guess, in some sense refined in different ways by some of the people here. Okay, good, that's the end of that.
So let me thank Rod for his nice talk. I think it was so nice that I even didn't notice he's already 10 minutes over time.
No, I started late.
No, I distracted him. I just took the 5 minutes back. So otherwise it would be 17. Any questions? So we still have time before lunch, I guess. If there are no questions, so you have heard a lot of exercises and homework here. I think those who were the experts, who roughly know why this should be true, so just to do it in detail, I would just lose a lot of blood if it comes to all that. So for those who are here just to get some flavor about the Cartan connections and Cartan geometry, I think that was quite good to follow. Now it's lunchtime. Concerning lunch, there is